Hello everyone. In this video, I'm going to tell you how to draw a layout. In IC technology, we have a process. Like first we start with an idea, then we try to do some hand calculation to get the basic parameter like W by L and all. Then we draw an schematic. After drawing a schematic, we draw layout based on that schematic. After that, we send our layout to for tape out, and after that we got a chip. So in this video, I am going to tell you how to draw this layout thing. So this also has various steps. Like first you draw the layout, and after drawing this you will check the DRC, design rule check, whether it has any error, is it fit for fabrication. So it tells all the things. There are some set of rules and it should satisfy all those rules. After DRC there is another thing called LVS. L stand for layout, S stand for schematic. LVS, layout versus schematic. So in this module we will check the whether layout and schematics are matching or not. I mean the ports and everything should be same. So after LVS we'll do PEX analysis, PEX. It will generate the parasitics involved in this layout. After drawing this layout we will get some parasitics and we should know its information because these are crucial. So we'll do PEX analysis. There are some other analysis as well like antenna check and ERC. So we'll tell you step by step. All right, I'll access it remotely. So I'll use SSH. All right, so now I'm in terminal. So for that, first I'll draw this schematic thing. So CSH, after that source, mentor.cshrc, and for schematic we usually type adk underscore DAIC. Okay, so it will take you to this window where you can draw the schematic. So for new schematic I'll click here and then we'll follow the same steps which you have already done. Okay, so maybe I'll create a folder here. Okay, so in this I'll draw this inverter. Okay, so this black window, in this window I'll draw the schematic. So after that I'll click ADKIC library. So in this library I'll get all the component like transistor, resistance, so I can use these. So for inverter I'll take this NMOS, after that PMOS. Okay, then I'll connect them. Okay, after that I'll use the probes, input, output, VDD and ground. So I'll give the name to these nets: in, out, VDD and ground. Okay, now I connect these nets with the schematic with circuit. Okay, so I'll save this. Check and save. There is no error. Okay, so after that I'll draw the layout. So for this uh, there is the command csh, then source mentor.cshrc, and after that I have to create one environment for this. So for that there is command adk underscore da not dve space then folder name. So my folder name is demo, in that inverter. Okay, after that minus t tsmc 018. So this is the command to create environment. So this is adk underscore dve, your folder name, minus t tsmc 018, enter. So this environment has been created, you can see it. Okay, so after that to open that layout window, I'll type adk underscore ic. So this will take me to the layout window. So here I can draw the layout. Okay, so I'll click on this new layout button. So this will come. So I'll click on existing viewpoint and will link my schematic with this layout. So on viewpoint, I'll browse this. I'll go to my folder, that is demo, then inverter, and then layout. Okay, and logic loading. So there are many options: flat, full hierarchy, and others. So you need to take care. You should click on flat. Then only you will be able to see the uh, various thing of layout, like diffusion and poly, everything. Okay, so cell name. In cell name, uh, I'll go to demo. Then I'll create one folder, inverter underscore lay. Okay, so in this inverter inverter underscore lay. So this is my cell name. Other things, next thing is process. So I'll browse this and we'll follow that path. $ADK, then technology, IC, and process. So in that, since I'm working on 180 nanometer technology, and I also created an environment for that only, so I'll use this TSMC 018 rule file. I'll follow the same path process. So I'll add the rule for 180 nanometer technology. So this is the file tsmc018.rule. Okay, so next thing is I'll go to option and I attach the library. So for that also I follow the same path in process tsmc018. Okay, so this schematic will open automatically. Okay, so to generate the layout, actually this process is to generate layout using a schematic. So we are generating layout. So with the help of this schematic we will generate layout. So you can see there are two windows now. So one is a schematic which opens automatically uh, after linking the thing, and this is your layout window. Okay, So here I'll generate the layout. So there is ADK. So I'll click on this ADK, show ADK palette. So on the right side you can see this palette. So here there is one switch auto instance. So I'll click on this and I'll get the layout. So yes, you can see here one PMOS and MOS. So I need to connect these things using metal and all. Give a brief about this. I'll take you to the one tutorial. So here you can visualize like this is substrate. Over it there's insulator, and after this there is written M1. So this is metal 1. So over this metal 1 again you will have insulator, then metal 2, and so metal 3, metal, so on and so forth. You can find different metal layers. Okay. uh, I would like to mention before, below metal 1 there is one layer called poly. So this is a sequence that generally layout rules follow. So layout is nothing but the top view. So if you will see this thing from the top, you see this is the side view, and if you see this thing from the top, so you can imagine structure something like this, two metal layers uh, on top of this. So this is layout. Okay. So these metals actually are, you can assume it like a apartment building. So the roof of the apartments are metals, and the side walls are like insulator. So to connect various components together, we use these different metals, because on a single platform we cannot connect all. We have to go up, then connect, and we can come down. Like you will get to know what are these things. So here they have shown one picture. So this is metal 1, then insulator metal 2, and the same thing which I was talking about. Okay. So this so okay, so for MOS, so this is the side view of MOS. So it has a P substrate, then N plus diffusion. So it should be of NMOS. So one is source, other is drain. Since it's a symmetrical device, so source and drain are interchangeable, and uh, after applying potential, then only you can identify which is source and which is drain. So this is gate. So if you will see this structure from the top, then you will get its layout. So let's see. Yeah. So this is side view, and if you see this from top you will find something like this. So these are diffusion, n plus n plus, and this is gate, which is made up from poly. So this is one layout of a MOS. So this is the layout of NMOS. So diffusion and this poly. So the same thing we got here also. So this is diffusion and the poly, diffusion and poly. So this is PMOS and this one is NMOS, right? So to give an idea how to connect these things, so I'll open this schematic window. So here you can see both the drains are connected together, and output is taken from this point. And similarly, both the gates are connected and input is given through this point. And for PMOS, from source VDD is connected, and from the source of NMOS, ground is connected. So similarly, we will connect in layout as well. So okay, so as I said, these are interchangeable, but still it is showing some idea how to connect. So it is saying to connect these two. So this may be source, or this may also be source. So if one is source, other one should be drain. So assume this is drain for PMOS. So we have to connect both the drains. So we will use metal to connect them, and we have to connect gate as well. So poly is gate. So we will connect these two together and we'll feed the input through this, and we will also use power rails here, VDD at the top and ground at the bottom. So for these things we have some instructions, some keywords, like to generate power rails I'll press space bar, then PR. So these are power rails. So I'll move these things down, so I'll select it. Okay, so I would like to mention here, to select it, you just click on this and it will get selected. And to unselect this you have to press F2, like this. You will use it frequently, F2, because many a times you have to unselect the things, otherwise if you are moving or deleting, so the things will get deleted. So you have to use this a lot, F2. Okay, so F2 is to unselect the things. Fine, so I'll select it, this one, and we'll move. To move I'll press M, so I can connect it with this. Okay, in the similar way, uh, I would also like to move this thing. So again F2 to unselect, then select these and M. Okay, F2. So now power rails are connected. Okay, so for the connection, I'll connect these drains with metal. So for this, space bar and M. So M gives me the metal. So I'll click on this and I connect it with this. So it's connected. F2. Fine. And okay, drain is connected to together. So the source side should be connected to VDD. So I'll again use metal space M. So I click here and I'll connect it. Okay, and the source of NMOS should be connected to ground. So space M. Okay. Okay, so this is done. So next thing is to connect these gates. So for this I'll zoom it, because thing is that these should be aligned. I mean, there should not be any edge error. So best way to zoom the things. Okay, so space P. So I'll click on this and okay, so this is connected. So I'll, to avoid any edge error, I'll see, yeah, it's connected properly. Fine. So these are connected. Okay, next thing is to generate ports. So like in a schematic you can see, so these ports in, out, VDD and ground, we need to generate these here as well. So for that, so we will go to the port. So there is one switch port. So if you click on this port, so it comes, it is showing output, it is written there. So maybe I'll use it here itself. Port. Another one is in, that's why it is connected to gate. So I am placing it here. Okay, so in and out ports. So to get their name, there is one option, port text. Where is port text? Yeah, it is there. So after click on this, I'll get the name automatically. So click, so here you can see VDD, in, out and ground. So it is clear, but here I would like to mention one beautiful concept. So you can see here, so first zoom it. You can see here, this is metal in blue color, and this is also metal in brown color, but their color are different. So what does it mean? So if you will see on the right side, it is written metal 1 in blue color, and if you move up, so metal 5 in other color, metal 4 in other color. So these are those metals I was talking about. So uh, so uh, now, although this metal 4 is placed on metal 1, but it is not connected. So to connect these things, I'll use via or via. Okay, so what is the concept of this via? So I'll explain you. Okay, so this is the thing which I was talking, metal 1, metal 2. So like from the bottom, poly, over it metal 1, metal 2, metal 3, so on and so forth. Generally we have 7 to 10 metals available from the foundry. Okay, so now, so this is the task, like I want to connect, because I have already told you that between the metals there is an insulator. So to connect these, suppose I want to connect metal 1 with metal 2, so I have to use via. So this is via. So this vertical connection is via. So in my problem, I have metal 1, and over on top of it somewhere I have metal 4. So I'll use via to connect between metal 1 and metal 2, then via 2 to connect between metal 2 and metal 3, then again via 3 as well to connect metal 3 to metal 4. So I'll use these kind of vias. So I need via 2 and via 3. So let's see how it works. Okay, so here I want to connect metal 4 with metal 1. So to generate this vias, so I'll press space, and for via I have a keyword pp. So this one. So now you can see this. So in this you can see two colors, uh, blue, and other one is I think yeah, this one. So this is metal 2. So some purple kind of. Okay, so blue and purple. So that means it is the connection between metal 1 and metal 2. Okay, so now we have reached to metal 2. So from metal 2 to metal 3, so we have to use another via, space pp. So for that you can change via here. So by default it will give you via via connection between metal 1 and 2. So to change it from metal 2 to metal 3, so I'll click here, I'll go to the end, and I replace this via 2. Okay, so now click OK. So it will give me another wire. So now you can see the color, like one is purple and other one is different, like this gray kind of thing. Okay, so this is the connection between metal 2 and metal 3. Okay, so I need one more connection to reach up to metal 4. So again space pp, and from the bottom I'll change it to via 3, enter. So this one, yeah, so this is the connection between metal 3, so this is the color of metal 3 and metal 4. Fine, so if I club these things together, so I'll get a connection between metal 4 and metal 1. Okay, so for that mm, F2, so I place this via, move it over this. Okay, then I'll select this via 3, press M, and okay, so now I'll select all together M and will place it here. Okay, and I'll copy this and I'll place the same thing here as well. Okay, F2. Fine. So I still need to connect this poly with this metal 1, because at the bottom I have metal 1, then I am reaching to metal 4. So my task is to connect this metal 1 with poly. Okay, uh, so I'll use M for metal. So it is connected. But the same thing, this metal 1 and poly are overlapping, but these are not connected. I have to use via again a via from poly to metal connection. Okay, so for that I have a poly contact. So that is PC space PC. So this is the one. So select it, press M to move this, and I can use it here. Okay. See, it's not necessary to place it at the middle. You can place it inside also, so it doesn't matter much because a connection is required. So that is the only thing. Okay. So I guess so. I'm done with all the connection, but still one connection remains. That is well contact. So I have to place well contact here, but I'm going with DRC, design rule check, because in the DRC I can see if I missed something. So this DRC will show me, or whether I have violated any rule, so it will show me that thing. So anyway, I'm going for DRC to show you how it works. So on the right hand side in this palette you can see this DRC is there. So click on this and check. Okay, so it is processing. It will give you the errors. Okay, so click on this. Okay, so here you can see the errors. Let's scroll it up. So it is showing total 4 results. So we have 4 errors. Okay, so to see what are these errors, click on DRC first. So this is one error. It is showing and well must have well contact. That's what I told you. So I'll place that contact. Next, uh, P substrate must have substrate contact. That's fine. We'll do that. Next. Okay, so here we have violated this rule. So metal spacing is 3L. So metal spacing should be at least 3L. This L is lambda. So these you have seen those dots. So those dots are lambda. The distance between two dots is L. So it should be at least 3L. So we'll remove this error also. Next. Okay, so these are the errors only. So I'll delete these errors, delete all. So now I'll change the thing. Maybe I'll zoom it. Okay, so 1, 2, 3. So that means it is counting this as a 1L. Okay, this thing is a 1L. Otherwise we have 1, 2, 3. Okay, so if we count okay, so here our metal is ending. So 1, 2, 3, 4, 5, and in sixth this metal is coming. So maybe we can shift it somewhat left, like small step left. So we will remove this error because 2 it's count as 1L. Okay, so for this I'll select this. Okay. So I'll select this. Oh, it's difficult to select two. So this, and this. Okay. So I'll press M and we'll move it to here. F2. Now again I'll see the error whether this DRC is removed or not. Check. Okay. Yeah, now it is showing only two errors, so I guess this is removed, but still let me verify first. So okay, well contact error. Next, fine. So this metal to metal spacing has removed, so I have to place well contact here. So delete all. Okay. So I zoom. So for that well contact, I'll press. So the, fine. This is N well for PMOS. So I'll place N well contact. So for this space NWC. So I'm placing it here. Okay. And for P well contact space PWC. All right. So I think now we should not have any error. So I'll again check DRC. Okay. Yeah. Yeah. Now total result is 0. So so our schematic is error free now. So DRC is clean. Okay. So next step is LVS. After DRC, we will do layout versus schematic check. So for these steps, for these process like DRC and LVS, PEX, ERC, and antenna check, we use this tool, Caliber. So, so if you go to tool, you'll find this Caliber. So here also you can use DRC. Next is LVS, then PEX, then other process. Okay, so next I'm going to show you LVS, layout versus schematic check. So in this I require two netlist. One is a netlist of layout and one is the netlist of schematic. Okay. Okay, so from here I'll check LVS. So I'll click on this run LVS. So this window will pop up. So here I need to give the path, so which should have the LVS rules. So it is following the same path from ADK to technology, then Caliber, and in Caliber there are many run sets. There are run set of LVS, there are run set of PEX. So I'll choose LVS here. So since it's already selected, so I'll click on OK. All right, so on rules itself, so there is another thing, LVS run directory. So I'll define my directory here. I'll browse it. So I'm in demo, inverter lay. Okay, so and input. So here I give the netlist of layout as well as the netlist of schematic. So this is the layout netlist. So this is the netlist of schematic. So generally, or I should say ideally, if I click on this export from schematic viewer, so my netlist should come here. My netlist of schematic should come here, and I can see it from the view. But I don't know what is happening. It is not coming. So other way is to generate it from the schematic itself. Okay. So for that, I'll use this schematic window. Uh, so this DAIC thing. So in this, go to simulation. So from here I can get the schematic netlist. So click on view netlist, then view netlist. So I can export this netlist export, and where I want to export is I can define okay, I want to export it in this folder. So lay, okay, yes, all right. So now I can view, yeah, it is showing this, but this netlist should be compatible with the netlist of layout, and in layout netlist we generally have sub circuit definition, so we should include that circuit definition here, and we should follow the same format. So I'll do the required addition. So go and edit. So I'll add the sub circuit definition. It's dot sub ckt, then my file name inverter underscore lay. After that the ports in, out, ground and VDD. Okay, and layout generally use ends, so I am adding it. Okay, since I'm not using VSS anywhere, so I'll change it to ground. G and D, because the body and source are connected. Okay, so now I'll save this, and then we'll run the LVS. Okay, so here you can see the netlist of for both for layout as well as for schematic. So in layout you can see the netlist here. So I added the sub-circuit definition in the netlist of schematic. This is because this schematic of layout contains this sub-circuit, and I have also added ends in the schematic netlist. So this was the reason. Okay, so next you can see it from here. This one is the netlist of schematic. This we have added in this thing, right? So now we can run the LVS. So this is LVS report, and it is not proper. It is showing some errors there, so we can see the discrepancies. So there are two discrepancy. One is, see, this source is your schematic, and this is the information of a layout. So this L and so these L and W's are not matching. Okay, so I should edit in the layout to make them equal, then only it will do the LVS check. Okay, so for simplicity I'll add it in the schematic netlist, but I should make any change in the netlist of layout. Okay, so I'll make the changes and I'll run it again, see what happens. So you can see from here, see the L is 1.8, that means 0.18 micrometer, and this is 0.45 micrometer. So I'm making the changes here. Okay, edit. Point 0.18 micrometer, 0.45 micrometer. 8. Okay, save it. Now it should be success, I think. LVS. Yeah, it's fine now. You can see this smiley. So everything is correct. So this is for your schematic, and this is for your layout. Ports are equal, nets are equal, instance everything is equal. So your LVS check is correct. So your layout and the schematics are matching with each other. Okay, and from here you can extract the various report. You can explore these things further. Okay, so next thing we are going to do parasitics extraction. So for that we'll do PEX analysis. Do the PEX analysis. So for that, I'll close this. Okay, so in tool, caliber, and run PEX. Alright, so this time here I'll be using the runset file path is a pex.tsmc. So since it is already there, so I'll click on OK. And for PEX run directory, I'll give the path of my directory, that is demo. Not exactly, yeah, till here. Okay. So in input we have this file. So output it will generate this here, but the netlist of my layout has the same name. So I'll change the name of PEX file. So I'll add PEX here. Okay, inverter underscore lay PEX.sp. So it will generate another file, otherwise it will overwrite. So now I'll run the PEX. So this is the final netlist from my layout. So using this netlist, I'll I'll do the simulation, like I'll do the analysis, like transient analysis or any other analysis which you want to perform. So this is my final thing. So it has all the information like LW and the area and the perimeter, everything it has. So using it, I can generate the waveforms. So to generate waveform, to simulate it, I use a tool called Eldo, and to generate to see the waveform, I'll use a tool called EZWave that you already aware with. Okay, so I'll close this. So okay. So to run this file, I should have one spice file in which I can include this file and will do the Eldo thing. So I'll show you. I have one file. I have already written that file. So it is there. So test.sp. So this is that spice file I was talking about. So in which I'll include the library here. Then the simple, it's a simple spice file. You already know. I forced the VDD. I have used a pulse here, and I'm doing the transient analysis. And here I'll include the name of my PEX file. Okay, so I'll copy it into my working directory. So I'm doing copy demo, then my file name inverter underscore lay, and here I want to copy this in this folder. Okay, so I'll go here directly and make the necessary changes if it is required. Yeah, it is there, test.sp. So I'll edit this, and since I have generated inverter underscore lay pax.sp, so I think it should work now. Hello test.sp. Okay, it is showing one error. Okay, so the error is unable to include file in it. Oh, we have given a wrong name. Actually, it was inverter underscore lay pax. So I'll correct it and run it again. Test.sp. So I'll correct inverter. Subcircuit also. Subcircuit we have inverter underscore lay. I think it should run properly now. Hello test.sp. Yeah, yes, zero error, and it runs for various steps. So to see its waveform, I'll plot ez wave. So I'll open this. Yes, here I can see the. So this test.wdb file is what I should open for transit analysis. This is in, this is out, so it's inverting. So here you can perform rise time, fall time, and other analysis. Okay, so but now what I want now, I want to see the difference between my schematic waveform output and the layout waveform output. So I'll overlap both. So now I'll simulate my schematic and we'll do the overlapping and we'll see the difference. For this we'll go to my schematic first and then we'll simulate it. So this is my schematic, so I'll simulate it and then we'll compare. So I'll include the library RTSNC 180. Then I'll force the various pins. So in is pulse. So there in layout netlist I used this pulse as with zero delay, and rest of the things are same. So I'll add it. Okay, so this PDD. PDD is TC 1.8. Add. Then ground pin. I think I should use this either bidirectional or as an in pin, because it's not out. But anyway, I don't know whether it will take it or not. Ground DC 0. Out is out. Okay. See the output. I'll select the pin and we'll add it. Apply the things. And for analysis, I choose the transient one. So let's see. Simulate it. Yeah. Zero error. So now I can generate the plot. So anyway, I want to generate plot that side with EZ wave thing. So leave it here. Open the earlier one EZ wave. Okay, so to generate the waveform of schematic, I'll open this. So this is our directory inverter here. So this is the file which contains the schematic WDB file. Open. Yeah, it is there. So I'll click this transient and I can see the output. So this is the output of schematic generated from schematic. So I can overlap these two outputs. So blue one is from schematic. So you can see these are exactly same with some delay at some points. So you can zoom this out and do the analysis. So our layout is pretty much good because here we are only using two MOS. One is NMOS and PMOS. So there is no much difference. So this is it about this layout thing. So you can explore it further. Thank you for watching.